Hi guys, welcome back to Primer's Classroom. In this class, we are going to be talking about the terms used in describing wave. Please, if you're here to watch class 1, endeavor to watch it before moving ahead with this class. Try to solve a lot of questions based on what you were taught in the last class. So now, in the last class, I gave you a definition of a wave. So I talked about what a wave is. I showed you the pattern in which a waveform can be seen. And in the last class, I gave you the classification of waves where we talked about the differences between mechanical and electromagnetic wave. We talked about transverse and longitudinal wave, and we talked about progressive and standing wave. So in this class, we want to quickly describe some terms that are used to describe waves. So the first term we'll be looking at is called the wavefront. So the wavefront is an imaginary line on an advancing wave where the particles of the medium experience the same disturbance. Now, remember the last time I told you that let's imagine we have a stone on a still water. We're going to have a ripple formed on that still water. Now, this ripple spreads out on the water surface. Now, there's a point on the surface of the water. Imagine I put a leaf here. Let's say leaf A and leaf B. As the water moves out, you see leaf A and leaf B moving up at the same time and moving down at the same time. So now, that point where leaf A and leaf B are experiencing the same disturbance is called the wavefront. So it is an imaginary line on an advancing wave where two particles of the medium experience the same disturbance. If I have particle C and particle D here, a point along this phase too, the energy you have here is going to be different from the energy you have here because the energy spreads out. So the kind of disturbance you have here and the kind of disturbance you have here, so that line where you're having the same kind of disturbance is what we call the wavefront. Now, the next term to look at is the wave profile. If you look at this ripple, the wave pattern on the side, you're going to see a particular pattern that it follows. So a graphical representation of wave in order to describe the properties of the waves and do some bit of calculations is what we call the wave profile. So this is a graphical representation. It follows what we call a sinusoidal curve. Now, this is the point of disturbance, then the wave travels out. So it's easier for me to talk about some things like calculations, be able to describe this waveform very well using this profile. So now, we always put our y here. Y represent the motion of the particles from equilibrium position up and down. Yx represent the motion of the wave along the horizontal axis. So the motion of the particles along the vertical axis is what I'm representing with y. Also, for a given time, the wave will travel out. So I can plot this y against t in order to measure the time at which the wave will travel out. So now, what are the things we need to know about this wave profile? So we have defined wavefront and wave profile. So now, there's another point called the crest. The crest. So this is a crest, this is a crest, this is a crest. Now, the highest vertical position is what we call crest, while the lowest vertical position is what we call trough. So this is a crest, this is also a crest, and this is a trough. So the highest vertical position is called crest, while the lowest vertical position is called trough. Now, when the particles of the medium, particle A and B now, they keep moving up and down from the equilibrium position, then they move up and down. So now, the maximum position that those particles can cover from its equilibrium position is called amplitude. So the next term we are looking at is amplitude A. Amplitude is represented as A, and the unit of amplitude is meter that you need to know. So it's meter. So it is defined as the maximum displacement from the equilibrium position. So that's amplitude. So this can also be your amplitude. It can also be downward or upward. So that's amplitude. The next term to look at is wavelength. Wavelength is the distance between two successive points. Note that between two successive points. If I start from here now, the next point that is going to start it is this point. So that means the distance from here to here can represent what we call my wavelength. It is represented by this symbol lambda. So wavelength is from here to here. Now, wavelength is also measured in meter. That is the unit. So you need to write that down. The unit of wavelength is meter. Now, I said distance between two successive points. Look at crest. Another crest is here. So the distance between two successive crests is also a wavelength. How about the distance between two successive troughs? That is also a wavelength. So you don't need to cram that. just know that a wave, if you start your wave, let's say you start it from here, then the wave moves once, half of a circle, then full circle. Then if it goes again, half of a circle, full circle. So I have two wave pattern there. So now when I start from here and I move from here to here, where I'm starting the second one, so the distance from here to here is going to be called my wavelength. So the next thing to look at is what we call the period or the frequency. Let's look at the frequency first. So the frequency is talking about the number of waves or the number of oscillation you have per second. So now frequency is given as number of oscillation per second. The unit of frequency is hertz. So it is measured in hertz. So the symbol is hertz. So don't forget, it can also be measured in per second. In per second. So frequency is measured in hertz or per second. What did I call frequency? Number of oscillation or number of circles per second. What I'm saying is that imagine I have a graph like this, and this time represents 1 second around this region. 1 second. Now the wave travels out and moves boom, 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 and it covers that. And imagine I have another graph like this, also in that same given time, 1 second. Now, but the wave moves so slow like that. Now, look at particle A and particle B. Which one do you think is going to have the highest frequency? It's going to be waveform A. Waveform A, we have the highest frequency because it has one, if you go 1, 2, 3, 4.5. So it has 4.5 wave pattern in 1 second. While particle B only have 1.5 wave pattern in 1 second. So the number of pattern you can form in a given second is what we call a frequency. So there's what we call period too. So if I move from here to here now, the time taken to move to complete just one oscillation is what we call period. The time taken to complete one oscillation is called what? Period. So if I move from here to here, so period is given as the time taken for one oscillation. Now let's do something here. Let's look at the difference between period and time, and period and frequency. Frequency and period. So frequency is given as n over t, meaning that n is going to be ft, right? Let's call this equation 1. And let's say period is also going to be time taken over n. So n is going to be t over capital T. Let's call this equation 2. So introducing equation 2 and equation 1. So I can have t over t to be equal to ft. So my t and t here can go. So my f can be equal to 1 over t. So you can see that frequency and period, they are reciprocals. So frequency and period is the reciprocal of frequency, meaning that the higher the frequency, the lower the period. So a waveform that goes so fast, that means it's going to take it a shorter time to cover one circle, just a very short time to cover one circle. But a wavefront that goes it's going to take it a longer time to cover one circle. So that's what that part is talking about. So the higher the frequency, the lower the time that you get. So now, if you look at this term, let's go back to circular motion quickly. Make sure you have written those formulas that I gave you. So, and those ones I'm putting in brackets, try to note those formulas. We'll be using them to solve some certain questions in the next class. So we remember from circular motion that omega is equal to theta over t, omega known as angular frequency or angular velocity, and the unit of omega is rad per second. Now for one circle or for one oscillation, your theta is going to be equal to 360 degree, and 360 degree can be represented as 2 pi in radian. So if I bring that here, that means my omega is going to be equal to theta, which is 2 pi. And you remember, for one circle, what do we have? The time taken for one circle is going to be what we call the period. So that's capital T. So from here now, I can say that my T is equal to 2 pi over omega. So let's note that formula as well. Now, if period is equal to 2 pi over omega, that means what will be my frequency? Frequency is going to be omega over 2 pi. So from there, I can say omega is equal to 2 pi f. So that is another formula to also note. Is that taken? So we link that from circular motion. So write that down and note those two formulas. So the next thing to quickly look at is what we call phase. So now let me show you something about phase. If I have a waveform or a wave profile like this, and you already know about most of these terms, so my x and my t, then my y representing the vertical position of the wave. So now from this wave profile, let's say I have point A, particle B, C, D, E, F, G, H, and I, J, and K. Now from this wave profile that I have here, you can hear the word phase or even phase difference. So we represent the term phase with phi. So that's phi to represent phase. Now, this phase is talking about two particles are said to be in phase when they move the same vertical direction or they experience the same disturbance. So now look at particle B and particle F. Both of them will be moving up and down, experiencing the same kind of disturbance. You can see the position and their direction will always be up and down like that. Same thing with J. So that means that B, F, J are going to be experiencing the same kind of thing. So they are said to be in phase. Look at A and look at E. You will see that the wave is starting from A, then another one is starting from E, then another one is starting from I. That means A, E, and I are going to experience the same kind of disturbance. So that is what we mean by A, E, and I are in phase. Look at D and H. They are going to experience the same kind of downward disturbance. So D and H are also said to be in phase. Do you think there's anyone that is also in phase? Very good. Look at C and G. If the wave moves half a circle and complete its circle, if this one moves half a circle, so C and G are experiencing the same kind of disturbance. So that is, I think there is K here. So that should be C, G, and K. So C, G, and K are going to experience the same kind of disturbance. So that is what we're talking about. So we have described all the terms used in describing wave. Now, another part to look at is what we call the speed, the wave speed. So when you talk about wave speed, you're talking about the distance covered for a given second. So speed is given as distance over time, and the unit for speed is meter per second. So now imagine I cover just one circle. That means the distance from here to here is going to represent what? Two successive points. That's wavelength. So I can say V is equal to my wavelength. And what is the time taken to complete one circle? Very good. That is my period. So that will be 1 over t. So I can represent this as lambda times 1 over t. And what is my 1 over t? Very good, frequency. So V is equal to lambda times frequency. So from there, there's a common wave equation. So the wave equation we have is called V is equal to F lambda. So you should not forget that wave equation in dealing with many problems. So in the next class, we're going to be solving questions on these parts that we have talked about from class 1 and class 2 so that you get used to them. Then from there, we'll move on to class 3 in the next class. So please endeavor to subscribe to this channel. Your subscription means a whole lot to us because that's going to encourage us to do more. And you leaving comments and letting us know the areas you want us to treat will also help us to do a whole lot for you. And please, we're here for you. We're trying to just bridge the gap between secondary school and the students. So after the school hour, when you get home, pick up this video, watch and practice some of the things your tutors have taught you, and you do well. So this is like a private class for you. So endeavor to sit down, rewind, go back over the video, get to understand it better. And please share it among parents so that all these parents can pass it on to their children while they watch at the comfort of their home and not being so bothered about traveling all around here and there. So that is it about waves, and I'll see you in the next class. So in the next class, we'll be talking about the properties of waves: reflection, refraction, diffraction, polarization, interference, and the likes. So I'll see you in the next episode.